Happy Thursday. It's a dreary Thursday, but perfect day to do math. What happened here? Oh dear. Right. We start Calc 3 by looking at vectors, both 2 vectors and 3 vectors, right? 2-dimensional and 3-dimensional. So there are several ways to represent vectors. You have the geometric interpretation, right? So directed line segment from an initial point to a terminal point. Then you also have what's known as standard form. Right? That's where the initial point is the origin. With standard form, you can then represent the vector in either component form or as a linear combination of the standard unit vectors, which anyone who's taken intro mechanics recognizes as I hat, J hat, K hat. Basic arithmetic of vectors, right? You have addition, you have subtraction, I use subtraction lightly, and then scalar multiplication, right? Technically speaking, subtraction is not a defined operation. We define subtraction as addition of -1 times, right? So b minus a is actually b plus -1 times a. Then addition is really simple, right? You just add corresponding components, right? And then scalar multiplication, also very simple. Just multiply each component by the scalar. So fairly straightforward stuff, right? This is like first grade level stuff, right? Adding and multiplying. Notice as of right now, we have not talked about multiplication of vectors or division of vectors. And in fact, there's no such thing as division of vectors. But there is multiplication. There's 2 products that we look at next week. Right, so the thing that distinguishes a vector quantity from a scalar quantity is vectors have both magnitude, which is a scalar, and a direction. Right? Scalars are obviously just some number. So your mass, for instance, would be a scalar quantity. Temperature is a scalar quantity. Speed is scalar. Velocity is a vector. Your position is also a vector. What we're asked to do first is we're given two vectors and we want to find magnitude and direction. And so we'll find magnitude of A, we'll find magnitude of B, and then for A plus B and then B minus A. Find magnitude of A. Since it's written as a linear combination of the standard unit vectors, right? That means that the initial point is the origin. So the distance formula is just going to be the square root of the sum of the squares of the components. Next would be 3 minus 0, which is just 3, and then 4 minus 0, which is just 4. Three squared 9, 4 squared 16, 9 plus 16, 25. And then the square root of 25 is simply 5. Finding direction, since this is a 2-vector, we're going to define direction as the angle the vector makes with the positive x-axis. let's go. Let's just call that our vector V. And so we're going to look for that angle there. Well, can't you represent that? The right triangle. That length would be X. That length would be Y. This would be the magnitude of V. So given that information, how would you find theta?
The one side of the right triangle, that's the magnitude of B or magnitude of A.
I'm just doing a generic V vector right now. Right, so I'm not looking at A right now. But it's just the magnitude of whatever vector you're looking at. Correct, right? So that's obviously then where the magnitude comes from. It's also the distance formula. But we're looking for theta. So how would that help us in finding theta? Right? Which one? Tangent. How's tangent defined? Right, so it'd be y over x. That's tangent of theta. Notice I'm not going to write theta as the inverse tangent of y over x. There's a reason for that. What is the range of the inverse tangent?
This example.
For A, yes, but in general, inverse tangent has a range of what? You have to think all the way back to pre-calc.
Pi over 2.
Open or closed? Right. Minus pi over 2 to pi over 2 exclusive of the endpoints. That's the range of the inverse tangent. That's quadrant 4 and quadrant 1. Oh, but by the way, minus pi over 2 to 0 is measuring clockwise, not counterclockwise, which is what we want. Right, so right there's a problem. If you take the inverse tangent and your vector's in quadrant 4, you're going to get a negative angle, which you do not want. If you take the inverse tangent, you will never get a quadrant 2 or quadrant 3. So if you just blindly type in to your calculator inverse tangent of something, and you just write that down, you only have a 25% chance of being correct. So just use the relation tangent theta equals y over x, and then we'll try and determine theta from there. Right, so for here, for A, let's actually do like tangent theta sub A to signify it's for the vector A. Our y would be 4, right? Our x would be 3. So tangent is going to be 4/3. That is quadrant 1, which is an angle between 0 and pi over 2, which means we can just safely take the inverse tangent. So the direction is the inverse tangent of 4/3. Leave it like that. Rule of thumb is you always leave your answers in exact form, unless either A, the problem specifically asks for you to round it, or B, some of the numbers in there were already in decimal form. Right, so if that 4 would have had a decimal after it, then we would approximate. Magnitude of B. Two squared plus -1 squared, square root of that. The square root of 5. And so for theta B, it's going to be given by relation tangent of theta is equal to -1/2. For vector B, what quadrant are we in? What is it?
Quadrant.
Fourth quadrant. Y is negative, X is positive. Right? You can actually just take the inverse tangent. It's just going to give you a negative answer. Like customary, we try to keep our angle between 0 and 2 pi. So just add 2 pi to it. As a rule, again, as a rule of thumb, it doesn't matter which angle you choose, whether you just take the inverse tangent, if you add 2 pi to it, it doesn't matter. Again, unless the problem specifically says, theta should be between, this and this. All right, now we need to find a plus b. Whether it's component form or unit or the standard unit vector form, it's the same way. You just add corresponding components together. So we look at the I components first. It'd be 3 plus 2. Then add the j components. Or plus -1. If it was a 3 vector, you would just then add the k components together. If you're dealing with a 10 vector, right, you just keep going. And it doesn't matter how large the vectors are. It's always done the same way, which of course means you cannot add vectors with a different number of components, right? So a 3 vector plus a 2 vector is undefined. I use, again, that very lightly because I can just say the 2 vector is a 3 vector where the third component is 0. 2 dimensions, yeah, 2 dimensions, 3 dimensions. Yeah. I mean, you have to be careful because if I do I plus k, that's a 3 vector. Right, because k hat is the third dimension. The j would just happen to be 0, so you'd have, let's say 1, 0, 1, right? That's a 3 vector. So when I say that, it's just what dimension am I working in? So a plus b would just be 5i plus 3j, right? So the magnitude of a plus b would be the square root of 5 squared plus 3 squared, right? Square root of 25 plus 9, 34. 34 is what, 2 times 17? So that cannot be simplified. So we'll just leave it as square root of 34. Notice a very important property. Magnitude of A plus magnitude of B is what? You're overthinking it. It's just 5 plus root 5. That is not root 34. Right, so that means that your vector length, right, it does not scale proportionally, or linearly, I should say, right, to the magnitudes of the individual vectors. So if you add 2 vectors, the resulting length is actually going to be less than or equal to the length of the 2 vectors. That is the Pythagorean, triangle inequality. That's it. It's known as the triangle inequality, which we will look at. I think when we do dot products, I prove it. So it could be equal, but not necessarily, but you'll never get a length greater. So tangent of theta is going to be given by what? It's going to equal what? Well, I'm asking you, is it? Three-fifths. What quadrant are we looking at? So we can just take the inverse tangent, right? So the direction would be given by the inverse tangent. 3/5. B minus A. Right, and this is where theoretical math and practical math diverge. Right, because theoretically, B minus A, that's minus is not an operation, so I have to write this as B plus -1 times A. For actual calculation purposes, that's not really practical to do, is it? Right, so for practicality, you can just subtract components. It works out to be the exact same thing. But if you're doing any kind of theory, you're not going to be allowed to do that. I think I'm going to do B plus -A just so I can get scalar multiplication in there somehow. And it's kind of like it's the same thing with Calc 1 when you looked at derivatives and integrals. Right, derivative is the limit of the difference quotient, which is a pain in the rear end to work with. And especially you have like a 20th degree polynomial, and, and I say, oh, here's this 20th degree polynomial, find the derivative using the definition. And you're not allowed to use a calculator to expand it either. It's going to take you a while. Integration's even worse, right? It's the limit of the Riemann sum. And if I say, go ahead and evaluate the integral from 0 to pi of sine of theta using Riemann sums, have fun. Trying to find a Riemann sum for sine is not fun. Oh, by the way, when we do multiple integration, we have double and triple Riemann sums to work with. You thought single Riemann sum was bad. Right, so B was what, 2i minus j? And then A was 3i plus 4j. There is an order of operations for vectors as well. Scalar multiplication must be done first. Right, and then addition. Unless the addition is inside parentheses. Right, so if that was -1 times the quantity of A plus B, then you'd add first, right? Oops, that's a minus j. So scalar multiplication, all you do is multiply each component by -1. Right, so that'd be plus -4j, which can also just be written as minus 4j. Now I can add them together. So we get 2 plus -3 -1, so -i. plus -1 plus -4, which is -5. So minus 5j. And again, that's why for all practical purposes, just do the subtraction. So tangent of theta is going to be given by what? Equals what? How'd you get 5? Right, so without simplifying, you'd have what? -5 over -1, right? You can just write 5, that's fine. I just write it out this way because then I can just look at that and go, oh, I know what quadrant I'm in. What quadrant are we in? Third quadrant means you're not allowed to take the inverse tangent. Because if you take the inverse tangent, you're going to get an angle in quadrant 1, not quadrant 3. So we have to add a correction. What would you have to add? That's just going to get right back to quadrant 1. Got your hand next. Pi. Right, and here's why. Let's say this is our vector here. That's the angle we want, right? That would be the vector that the inverse tangent gives, or the angle that the inverse tangent gives, right? So how do you get from phi to theta? Well, that's just a line, isn't it? So just add pi. So it's pi plus the inverse tangent of 5. Because that was quadrant 4, right? So I added 2 pi because I wanted an angle between 0 and 2 pi. If you take the inverse tangent of -1/2, it's going to give you a negative angle, right? Because the range is minus pi over 2 to pi over 2. Again, that part wasn't necessary. You could have just left it as a negative angle. I like my angle between 0 and 2 pi personally.
Different issues.
Yes. So it's not always, so every problem's not always going to be like the same. That's why I said you can't just blindly do the inverse tangent. You actually have to look at the problem and think. Tell everyone, calculators are great, right? Technology is wonderful, but it's only as smart as the person using it. That's good. You know what? Let me turn that annoying feature off. Hide authors. Also, with the study of vectors, we kind of looked a little bit at the space, the three-dimensional coordinate system as well. And three-dimensional coordinate system is very easy to create, right? You just take your X and Y axis and add a third axis that is perpendicular to both. And that's how you get your Z axis. Typically speaking, it's represented this way. Right, so the convention is to let Z represent your height and X represent your depth. And then Y would be length. As long as this is a right-handed system, it is still valid. So you could just rotate all of that 9 degrees, right? You could have X being length, Y being height, and Z being depth. Doesn't matter, but this is the standard way, and that's how I'm gonna keep doing it, just to be in line with all of the texts, even though that's not how I learned it. By the way, if I wanted to go into the fourth dimension, it's done the same way. You just now draw a fourth axis that's perpendicular to all three of them. Then the fifth dimension, you just draw a fifth axis that's perpendicular to all four. Since we are just three-dimensional beings, you cannot visualize what the fourth dimension or higher looks like, right? Which is why you're making that face. How would you draw a fourth axis perpendicular to all three? It's very easy in the fourth dimension, right? You just draw in the fourth dimension. But how do you, what does the fourth dimension look like? We can't think about that. And I'm not talking about the dimension time. When I say fourth dimension, I do refer to spatial, which is why we call time the 0th dimension. Yeah, mine. And string theory works in 9 spatial. Go ahead and try and imagine that. Really good. There was a really good novel written on it, Flatland, which does a really good job of explaining higher dimensions in a fictitious way. So it's an actual novel. It's not like nonfiction. And it has a sequel. What's it called? Not Space? No, Spaceland? I think it might have been Spaceland. Right, so Flatland kind of deals with, oh, you're a two-dimensional being, and it's trying to explain how the third dimension works, which you can easily visualize. Then the sequel is now 3 dimensions trying to explain the fourth dimension. So it's analogous. All right, so we're now working essentially in 3 dimensions. We're working in space. Technically speaking, everything we're going to be learning is a lie, because we're assuming flat. I hate to break it to you. Our universe is not flat. Space-time is curved. Specifically, it's curved as a sphere. So all this is technically a lie. But for short distances, you can approximate it as flat. Right? Your table's not technically flat, right? Because the Earth is curved. So there's actually a slight curve. But that curve is so slight that we can approximate as flat and get a really good answer. By the way, all physics that you're learning is a lie as well. You don't actually learn true physics until grad school. Everything else is a lie that just keeps building on itself. Well, I didn't go for a master's in physics. I gave up. I said, why am I doing this to myself? All the concepts you learned of the plane, right? Distance between 2 points in the plane, right? The axes, how everything works, just naturally extends into the third dimension. So if we want to find distance between a point in space or between 2 points in space, the formula is identical. You just add the third component. Z minus Z naught squared under the square root. Right? So distance from our point P to the origin. Just be the square root of 1 squared plus 2 squared plus 3 squared. That's the square root of what? 1 plus 4 plus 9, which is 14. Root 14. 14 is 2 times 7, so that cannot be simplified. Represent the x-axis. This. Yeah, I'll just do that. So distance between the point and the x-axis. So what we want is the shortest distance between the point and the x-axis. Right? Because technically speaking, you have an infinite number of distances. Well, the shortest distance would be when the x components are equal, right? So we just choose the point 1 on the x-axis and find the distance from that point to our given point. There's be the square root of 2 squared plus 3 squared. 4 plus 9, 13. And 13 is clearly prime, so.
So you got that by subtracting 1 from the x, because the 1.
Right, yeah, it'd be 1 minus 1 squared for the first component, which is 0.
And then
Yeah, and then it's really just, you look at y and z. And that's true no matter what axis you're working with, right? So now we're dealing with the z-axis. You want to choose your point in the z-axis that equals the z component, right? So we're going to be at the point 0, 0, 3 on the z-axis. So really just eliminate the z-axis. The distance would be root 5. Fine, thank you. Right, so now distance from the point to the xy plane. Again, we're looking for shortest distance. Yes. What you're really doing, right, is taking the distance from the point and its projection on the XY plane. So it's you can think of it like its shadow on the XY plane. Well, that's simple. That distance just be, okay, how high is it off the XY plane? 3. Right, and then the distance from P to Q, or Q to P, whatever, doesn't matter. So the square root of right, 1 minus 3 quantity squared, 2 minus -1 quantity squared, 3 minus 5 quantity squared, and then take the square root. That would be the distance between P and Q. Q is the 0.3 -1, 5. I'm just going to go ahead and get rid of the negatives. I'm just going to write everything as positive because you're squaring it anyway. 2 squared plus 3 squared plus 2 squared. 4 and 4 is 8. 8 and 9 is 17. So the distance is square root of 17 units. And again, 17 is prime, so that can't be simplified. Yes.
The Z.
This here?
Yeah.
It's the Z component of P minus the Z component of Q, right? Oh, you're reading that as negative 1.5? So we're given 3 points and we're told they form a triangle. We're asked to find the distances between each pair of points and then go back to English class to learn how to spell. And then determine if the triangle is a right triangle. So I'm a math major, I don't need to know how to spell. I'm surprised it's not giving me a red line of death. Oh, now I saw it. Okay. All right, so distance between pairs of points is the same as the magnitude of the vectors. All right, so vector AB, just find its magnitude, that'd be the distance between A and B. Get what? Square root of 2 minus 1 squared. Plus the square root of 6 minus 4. I'm sorry, 6 minus 4 quantity squared, and then plus 3 minus 2 squared. So it should be 1 squared plus 2 squared plus 1 squared. Which is what, root 6? Find the magnitude of vector AC. Notice we don't have to do the magnitude of BA. Right, because the magnitudes are going to be the same. The only difference is the vector was flipped 180 degrees. Four minus 1 squared, so 3 squared, 3 minus 4. Negative 1 squared, and then 1 minus 2. Negative 1 squared. 9 plus 1 plus 1. Root 11. And finally, the length of the vector BC. Square root 4 minus 2 squared plus 3 minus 6 squared plus 1 minus 3 squared. Four, 4 is 8. 8, 9 is 17. Square root of 17. How are we going to determine if this is a right triangle? How do you know which one is A, which one is B, and which one is C? If that is true, then we have a right triangle. What is root 6 squared? Right, and obviously root 11 squared would be 11. So 6 plus 11 is 17. The question is 17 the square of root 17? It is. So this triangle is a right triangle. Here we want to write each vector in component form and as a combination of the standard unit vectors. So let's just take two arbitrary points, P and Q, x0, y0, and then x1, y1. Standard form simply means the vector's initial point is at the origin. Beautiful thing about vectors. As long as direction and magnitude are the same, does not matter how you draw it. So it does not matter how you set up your coordinate system. So there's P prime. In standard form, right, your vector is just the terminal point. That looks to be the same direction and length, so we'll just say that. P prime is clearly 0, 0. What's Q prime? So explicitly tell me, what would the x coordinate for Q prime be? Not using the problem, just from these arbitrarily chosen points. Right? Since length and direction have to be the same, whatever you do to point P, you also have to do to point Q. That is how you get component form. So component form, be the Q coordinate minus the P coordinate, depending on what component you're in, right? So for X, it would be 7 minus 3. For Y, it would be -2 minus 2. You get 4, -4. And then this is where you need to keep notation in check. Because in linear algebra, that is not how you would write a vector. Right, linear algebra would be this. Or depending on the text, I've also seen text write the vector this way, which I just absolutely hate. Then I just go, no, that's an ordered pair, not a vector. Ordered pairs are points. I will not be using either of those notations in this course. And then physics, of course, never uses this form they like, for some reason, the standard unit vector form. Don't know why. Probably just to make life miserable. Once you have component form, finding it as a linear combination of the standard unit vectors is really straightforward. I'm actually going to work out how you can get to it, and then I won't ever do that again. So using the definition of vector addition, can't we write that vector as this? Right? So those vectors are now decomposed. And then by definition of scalar multiplication, right? Well, isn't this vector here I? And this vector here is j, isn't it? So yeah, 4i minus 4j. Which you can easily see from component form. So like I said, I'll never do that again. Yes. No, that is linear combination of the standard units. Where's my mouse? This is component form. They can be used interchangeably, right? Doesn't matter. However, the rule is whatever form the problem gives the vector in is the form you want your answer to be in. And so what I typically do is I will always write it in component form to do the arithmetic because it is a lot easier than constantly writing the IJK. And then at the end, I'll then convert it if I have to. Well, wouldn't the idea be exactly the same in 3 dimensions as it is in 2 dimensions? Right, it's just you now have that third coordinate to work with. So component form, wouldn't we get the first component, the x component, to be 4 minus 2? The y component would be 3 minus 1. And then the z component would be 2 minus 2. So 2, 2, 0, right? Should be 2i plus 2j plus 0k. You're allowed to just drop that 0k. However, there is a problem if you drop the 0k. Right, if all you were given, for now, let me do this. Is that 2 dimensions or 3 dimensions? So is that a vector in the plane or a vector in space? Don't know. Right, so be careful when dropping the k. Context. You'd have to have context. So you right, so obviously then in the context with the problem, you know it's 3 dimensions. By the way, that's true for a lot of math and physics, right? Context is everything. Find the unit vector in the direction of that v. Right, so what is a unit vector? What's the definition of a unit vector? Look at I hat. 1, 0, 0. What special property does that have?
That's direction.
True, but why is it specifying a direction? Like, so why wouldn't we use, for instance, 8, 0, 0?
Because it's, when you multiply by the scalar value, it gets you that value.
Right, so what special property does that have? That one is important. So look at what we studied so far today, right? We looked at what? Addition, scale multiplication. We looked at directions and magnitudes. Well, clearly we can't deal with addition or scalar multiplication here, right? Because it's just 1, 0, 0. We know the direction. So what's the magnitude? Well, just the magnitude of 1, 0, 0. Using the formula. It's just 1. What about J hat? Which is 0, 1, 0. What's its magnitude? What about K hat? 0, 0, 1. What's its magnitude? So what's a unit vector? A vector of length 1. Whenever you hear direction vector, it should always be unit, right? You only want the vector to tell you a direction, not to change magnitude. The only way to not change a vector's magnitude is if the direction vector itself is unit length, because 1 times anything is just itself, right? That's why we can't use 8, 0, 0 as I hat, because that would change the magnitude of the vector. So that's what we want to do here. We want essentially the direction vector for V. Right? When we get into partial derivatives, we look at what's known as a directional derivative, which is a rate of change in a specific direction. We're going to need to know how to do this. Sadly, we are out of time. So tomorrow, I didn't mention this, we are only required to meet 200 minutes a week. Well, if you actually do the math, that's scheduled, right? Tuesday, Thursday, Friday, it's 75 minutes each meeting. That puts us well over 200 minutes. So typically speaking, Fridays are going to be 50-minute classes, unless I really need the extra time. So Fridays will generally always be shorter classes. I think it will be 9:30 to 10:20. So tomorrow we're just going to finish up. There's only 2 problems left. There's this one, there's one more problem, and then it'll be your quiz on this stuff. See you all tomorrow morning.